నేను మొన్న వస్తున్నాను. ఓకే, గుడ్ మార్నింగ్. గుడ్ మార్నింగ్. So here we have the presentation. Okay. So good morning to all. Government Polytechnic Husnabad, Electrical and Electronics Engineering, Digital Electronics, Nedunuri Parameshwar, lecturer. Okay. So my name is Nedunuri Parameshwar. I'm working as a lecturer in Electrical and Electronics Engineering, and my institution is Government Polytechnic Husnabad, Siddipet district. Now I taught the subject digital electronics. So the subject code is 18EE405C. C means that is core subject, so purely related with electrical department and electrical section. Okay. And next, today the objectives are to define a combinational circuit, and now we are starting the third chapter, that is combinational circuits. Okay, so that is the combinational circuits. So today objectives are okay, define combinational circuits, to develop the logical diagram of a half adder along with the expression truth table output, realization of half order using NAND NOR gates, develop the logic diagram of a full adder along with expression truth table output, realization of full adder using half adder and basic gates. So today we are completing this define combinational circuits and develop the logical diagram of a half adder along with expression truth table output, and next realization of half order using the NAND and NOR gates. Okay, and develop the logic diagram of a full adder along with the expression truth table output. And these four are the tips we are completing today. Okay. The next one is combinational circuit. The first topic is combinational logic circuits. Okay, combinational logic circuits. A logic circuits which has no memory, no feedback from output to input, and the present output depends upon the present input. So this logic circuit is called as combinational logical circuits. Okay. So here the we have the topic combinational circuit, combinational logic circuits. So already we are discussing logic gates in previous lesson. So what are the logic gates we have? The basic gates, universal gates, and special gates. With the help of that logic gates, we are forming a circuits or networks. Okay, so we have the basic gates, AND gate and NOR gate. So with that NAND gate and NOT gate, For example, okay, we are taking one example. So, for example, I have a NOT gate like this. Okay, this is the NOT gate, and next and have we have AND gate, AND gate like this. So I have NOT gate and also have AND gate. So with these two gates, I form a circuit. So simply, for example, I draw this cover combination. Here we have different gates. The what is one is NOT gate and another one is AND gate. This AND gate and NOT gate are connected like this. For this one, AND gate and NOT gate. And these two are connected like this. Okay. So this is one combination circuit. We are connecting these two logic gates are here. So this is the one example for the logic gate, logic circuit. So here we are giving, for example, AB. AB is the input, and we are getting AB here, and we are connecting NOT gate here. So the ultimate output is AB bar. So that is the output of NAND gate. Okay, this circuit also represents the NAND gate. So here, get this a logic circuit which has no memory and no feedback. There is no feedback from output to input. Okay, and from output to input. The present output depends upon the present input. If we have here 0, 1, okay, depends upon these inputs, we are getting output. If we have 1, 0, so in first case we have 0, 1. So 0, 1 and get output is only 0, output is 1. For example, we have the input is 1, 1. 1, 1 for the AND gate, we are getting 1. For NAND gate, we are getting 0. So depends upon the inputs, we are getting outputs. So here, output depends upon the present input. So this logic circuit is called combinational logic circuits. Okay. So a logic circuit which has no memory and no feedback from output to input, and the present output depends upon the present input. So this is called logic circuits. So next, combinational circuits black diagram. So this is the black diagram of combinational circuit. So here we have number of outputs, number of inputs, A, B, C. So up to we are getting n number of inputs. So this ABC is called as inputs, and this A bar, B bar, C bar represents the outputs. And here we have number of inputs and number of outputs. So in this combinational circuit, in this blocks, we have different gates like NAT, NOR, and so whatever it is. So we have the different inputs. So we have number of inputs and number of outputs here. Okay. So this is about combinational circuits, combinational logic circuits. Okay. So next, coming to half adder. Adder. What is mean by adder? Adder is nothing but okay. So here we have half adder. So half adder, the main name itself adder. Adder is nothing but it's adding the two binary inputs. So here a logic circuit that adds two binary bits is known as half adder. So two binary bits. Binary bits is nothing but we have only two, that is 0, 1, 1, 0, 1, 1, 1, or whatever it is. So these two binary bits is binary bits are added in this logic circuit. So that logic circuit, that combinational circuit is also known as half adder. Okay, a logic circuit that adds two binary bits is known as half adder. The function of half adder is to add two binary bits and produce outputs sum and carry. Okay, so here we get sum as well as carry. We are getting two outputs and we are giving two inputs for half adder. So this is the block diagram of half adder, for example. So here we have two inputs, that is one binary bit and another binary bit, and we are getting two outputs. So we are representing with A and B, for example. So these two inputs, and here we get two outputs, that is one is sum and another one is carry. Okay, so this is about half adder. The function of a half adder is to add two binary bits and produce two outputs. Okay, so this is the block diagram of half adder. So in this half adder, we have inputs A, half adder inputs we have A and also have B. So here we have two inputs, and next we have one AND gate. So this is the logic gate, AND gate, and another gate is XOR gate. So XOR gate. XOR gate is nothing but this is the A, B bar plus A bar B. So this is the XOR gate output. Okay. So here the we have for to form a logic circuit of half adder, we require two gates. So those gates are the AND gate and XOR gate. One is AND gate and another one is XOR gate. Okay. So two gates are required to form a half adder. And next AND gate output represents the carry. So that is A dot B, A into B. And next XOR gate output is represents the sum, that is A XOR B. Okay. So this is the half adder circuit. So half adder, we have two inputs AB and get outputs to sum and carry. In carry we are getting A into B, and in sum we are getting A XOR B. Okay. And next half adder block diagram is here. This is the A input and this one is B input. This is the half adder circuit. So in this half adder circuit we have two gates, that is AND gate and XOR gate. So here we are getting the sum output and carry output. So these are two outputs and these are the two inputs. So next we are giving the inputs A, B. So let's check the truth table for the and fader. Fader truth table is, so we have the two inputs. No? The possible number of possible inputs are four cases. Those are the 0, 0, 0, 1, 1, 0, 1, 1. So these are the possible cases of two inputs. We have four possible cases. That is the 0, 0, 0, 1, 1, 0, 1, 1. Okay. And next output we have sum and carry. And so those are the we are discussing here. So in first case, so this is the first case. So in first case we have 0 A and B. So this 0 we have here 0 and here also we have 0. Simply for XOR gate, for same inputs the output is low and for different inputs the output is high. So this is the XOR gate logic. So the logic for the XOR gate is simply for the same inputs we are getting output is low. For different inputs we are getting output high. So for this same 0, 0 we are getting output here 0. So that's why we are getting the sum is 0. And next this 0, 0 comes to AND gate. So AND gate inputs are 0, 0. The AND gate logic is when two inputs are high, then only the output is high. When two inputs are high, then only the input is high. So here we have the inputs only 0, 0, that is low inputs. So that's why we are getting the output is only 0. So that is the carry. The output of the AND gate represents the carry and output of the XOR gate represents the sum. So the carry is this one. So in second case, at the second place, or to second case, in we have the 0 and 1. 0 and 1. So here we have 0 and 1. So these are the different inputs. So for different inputs we are getting here two different inputs. So we are getting the output is 1. Different inputs output is high, same inputs output will be low. So that is the logic of XOR gate. So for inputs of 0 and 1 we are getting the sum is 1. And next coming to the carry. So for carry here we are giving the input is 0 and AB A is 0 and B is 1. So for AND gate, the logic is when two inputs are high, then only the output is high. So here the one of the input is low, so that's why we are getting the output is also low. So that is 0. So here getting we are the 1 and here then 0. Okay. So the output of the carry is 1, 0. Okay. So for third case, so we have 1 A and B is 0. So here 1 and 0. So for different inputs, ultimately we are getting the output is 5. So that is 5, 1. And next to, and also we have 1, 0. So for one of the input is low, so the output is also low. Okay, that is 0. And next we have the fourth case. So this is the third case. So for fourth case, we have the inputs 1 and VA also 1, B also 1. So here we have the inputs 1, 1, 1, 1. So for same inputs, the XOR gate output will be 1 only. Oh, so not 0. The same inputs, the output will be low. For different inputs, the output will be high. So here we have the same inputs. So that's why we are getting the output is low, that is 0. And next we have the AND gate. So for AND gate, when two outputs inputs are high, then only the output will be high. So that's why two inputs are high, so output will be high. So this is the truth table for the AND half adder. So for the half adder, the sum is, so in normal cases, 0 plus 0, 0 only. So it's correct. 0 plus 1, 1 only. And next to 1 plus 0, 1 only. And 1 plus 1, we have the sum is 0 and carry is 1. So in these three cases also, we are getting a carry is 0. So the truth table shows the correct results. Okay. So this is the perfect thing. So this is the half adder block diagram, and this one is the half adder logic circuit. So in this logic circuit, we have two gates, and one is XOR gate and gate, and we have two inputs and two outputs. So that is A and B, and sum and carry. So these two are outputs. Okay. And next, we have the topic is the realization of a half adder using NAND gates. Realization of half adder using NAND gates. Realization of half adder using NAND gates. So in previous slide, we already, so here we have the half adder circuit, XOR gate and gate. So in this XOR gate and AND gates are represented by NAND gate. Okay. So how it is possible, and what is the output of sum is like A XOR of B, and output of carry is A into B. So for this, we are using only NAND gates. How can it possible? You can see. So, so first we have the input is A, and here we have input B. So A B. So for this A B, we are the output is A B bar. Here we are getting the output is A B bar. So this output of AB bar is directly given to NOT gate, which is represented by NAND gate. So AB bar of bar. So here we have two bars. So ultimately the output is AB. So we are getting the carry like this. C equals to A into B. So that is C is nothing but carry. And next here we have the AB bar is one of the input for this NAND gates, and A is another input of the NAND gate. So that is A into AB bar, A into AB bar of whole bar. And next here we have the, and here we have the uh, one of the input of this NAND gate is B, and another one input of this NAND gate is AB bar. So AB bar and B of into total NAND gate. So these two outputs of these two NAND gates are given to this number 3 NAND gate. Okay. So here we are using 1, 2, 3, 4 NAND gates, and another NOT gate which is represented by NAND gates only. NAND gate. So further we are using 5 NAND gates by realization of half adder by using the NAND gates. We are using the 5 NAND gates. So these two NAND gates outputs will be connected to this NAND gate, and we are getting the input output like this, A into B bar. So after simplification of this total equation, we are getting like this, A B bar plus B A bar B. So that is equals to A XOR B. So that is the sum of this half adder. Okay. So this is the realization of half adder using NAND gates. This is the realization of half adder using NAND gates. Okay. And next realization using the realization of a half adder using the NOR gates. So here write this. Okay. So here we have A and B. So A and B with NOR gate. NOR gate is nothing but simply A plus B whole bar. So this is the output here. And next here we have A with A NOT gate. That is here we are getting A bar, and here we are getting B bar. Okay. So A bar and B bar plus here directly we are getting A bar plus B bar. Okay. So that is whole bar. So directly we are getting, after simplification of these two, we are getting only AB. So that is equivalent to carry of half adder. Okay. And next here you observe this one, here we have AB as input, and next here we have A plus B, A plus B bar as input of XNOR gate. So after this, we are getting AB plus B bar. A plus B bar అనొచ్చు, లేదంటే okay, A plus B bar of whole bar. So after simplification of this total equation, we are getting here A XOR of B. A XOR of B. Okay. So this is the realization of half order using NOR gates. Realization of half order using the NOR gates. Next, coming to the so next the topic is for adder. So the full adder. So for full adder we have the so up to now we are discussing about half adder only. In half adder we have only two inputs and we are getting two outputs. But in full adder we have three binary inputs at a time is known as full adder. So in half adder we have only two inputs, but here we have three inputs. So that is A, B, C. So these three bits are added at a time only. That is the full adder. And next, the function of a full adder is known is capable of adding three binary bits and produce the output is sum and carry. So here the inputs are A, B, C, three inputs, and outputs is sum and carry. Okay. So this is about full adder. And let's see the output of block diagram of a black diagram of a full adder. So here the C represents as carry in, that carry in. So this is input, and next this is output. So here we have full adder circuit. Here we have full adder circuit, but this full adder is nothing but one full. This full adder is represented with two half adders. So half adder is nothing but simply. So in half adder we have XOR gate like this and AND gate like this, and also here we have XOR gate and AND gate. So this is the one half adder circuit, and this one is the another half adder circuit. And here we have carry in, and we have extra input. So that is carry in. Carry in, that is this one. And next here we have the output. This is directly giving the uh, another using the OR gate. We are using extra OR gate to get carry output. That carry output is coming from AND gate only. Okay, so here AND gate. So the AB, here we are getting AB. So the output is A of A XOR of B, and we are getting output is BAB. So this AB is directly coming to this one. And next here we have the AB, A plus B R of C. So that is A plus B R of Malli equal C, and we are getting the output as like this: A plus A XOR of B XOR of C. So this is the output of the sum of the full adder circuit. And next carry we have here AB. Okay, and next here we have A plus B of B. That we are the outputs are AB plus BC plus CA. So these are the we have. So this is the carry output of a full adder circuit, and this one is the sum output for the full adder circuit. Okay, so this is the block diagram of full adder circuit. In this full adder, we have two half adders in addition to the OR gate. Okay, so this is the connection diagram of full adder circuit, and let us see. So here we have the full adder circuit, and next the output here we have, for example, so this one we are taking here A is the input and B is the output, so input and C. So for this A and B, so this A and B are connected like this. This A, okay, is going here. So here we are getting A. And next this B is directly connected to here. So this is B. So the output is AB. Okay. And next we are getting B here. Next B here. So we are getting here B and C. Next here we have C. And next this one A. So we are getting here A C. So the ultimate output is AB plus BC plus AC. So this is the full adder carry out. The carry output is like this AB plus BC plus AC. And next here we have the input to A and B. So here we are getting the output is A XOR of B. And next directly we are getting here C input. The output is like this A XOR, XOR of B XOR of C. So this is the sum output of this full adder. So in this full adder, we are having inputs A, B, C, and outputs are sum output and carry output. A XOR of B XOR of C, and here AB plus BC plus AB plus BC plus AC. So this is the output. Okay, and next full adder circuit this one, and next we have the full adder circuit truth table. Okay, for this truth table, simply here we have the 0A input, B 0 and C 0. So 0 plus 0, 0, 0 plus 0, 0. So the sum is 0, ultimately the carry is also 0. And next we have the input 0, A, B, C, 0, 0, 1. So 0 plus 0, 0, 0 plus 1, 1, and carry is 0. And next 0, 1, 0. 0 plus 1, 1, 1 plus 0, 1, and carry 0. And next 0, 1, 1. 0 plus 1, 1, 1 plus 1, 0, and carry 1. 1, 0. 1 plus 0 is 1, and 1 plus 0 is 1. Sum is 1 and carry is 0. And 1 plus 0, 1. 1 plus 1, 0, and carry is 1. 1 plus 1, 0 sum and carry is 1. That sums 0 plus 0, we are getting sum 0 only. Okay. 1 plus 1, we are getting carry 1 and sum is 0. That sum 0 plus 1, we are getting 1 only sum. So this is the truth table for the full adder circuit. This is the truth table for the full adder circuit. Okay. And next, thank you for the listening class. Let us see how much. So today we are completing the covering these objectives, combinational circuits, define combinational circuit and develop the logic diagram of half order along with expression to table output and realization of half adder using NAND and NOR gates, and develop the logic diagram of full adder along with expression and truth table. And here we are don't cover this realization of full adder using half adder and basic gates. Okay, this is also covering full adder using half adder. So we are using two half adders and also with one OR gate. So this is the diagram for that. Okay, two half adder circuits and one OR gates. So this is also covered, and this is the full adder circuit. Here we require two XOR gates and three NAND AND gates and one OR gates. For full adder circuit, these are required. And next, okay. So thank you for staying at home and stay safe. Okay. Okay, this is about our slide. Government Polytechnic Kushnabad, Electrical and Electronics Engineering, Digital Electronics. Okay. So ultimately, it's not so custom slide. Okay.